In this third installment, what we're going to do is we will give you a quick introduction to the 5 key steps in hypothesis testing. So let us get going on that right away. Your book has a slight different variation of that, so let's take a look and see how we're going to set it up. So step 1, we have 5 steps. The first step is to state your hypotheses. Okay. So our hypothesis HO and HA. So we will have HO, HA, and remember HA is what we want to prove. HO is what we're going to assume is actually true. Okay. And step 2, we need what we call a test statistic. The test statistic is how we're going to measure the evidence. And in our case, we use either Z or T, depending on what the sampling distribution is. So if the population standard deviation is known, we will use a sampling distribution that is normal. If it is unknown, we use a sampling distribution that is T. So it's either Z, the observed Z value, would be X bar, if we're dealing with hypothesis test for the mean, minus mu sigma over root n, or it would be T, X bar minus mu S over the square root of n. Okay, so either one of those two, and of course with degrees of freedom n minus 1. So that's our test statistic. It measures for us the evidence. And the bigger the Z value or the T value, the more evidence we have. And the way to think about that is to think about it in terms of the bigger those values are, the more the sample is different from the population. So if we think about the case when we talked about exams, and the average exam mark is 66%, but we got a random sample of 50 individuals with an average of 80%. And we got that was a Z value. We measured that evidence in terms of Z, and that was a Z value of 5.5. So you have to say, whoa, this is fairly different, away from the mean. 5.5 standard deviation. So therefore, it cannot be, a representative of that population mean. It's kind of like the example I gave you. If somebody sent you a box of oranges, but then you pull out mostly apples, it's too different, all right? So we measure the evidence by those. And if we just take them and convert them to a probability, that's also evidence, because you recall that I went back to chapter 7 to calculate probabilities to tell you that when the further a sample is away from the mean of the population, or the assumption that we've made, the smaller the probability also is associated with it. That probability associated with that will also be small. So 5.5, the probability in the tail is less than 0.001, which means that the event is significant. Remember we said small probabilities are significant because they're not supposed to happen. All right? So that's our test statistic. We measure it with Z values or T values, or the probabilities associated with these values. Then we go to step 3. Step 3 is a decision rule. And basically what we do is we take the sampling distribution and we set a boundary. Now, we started off when we were talking about empirical rule and Z scores, saying that values of Z of 2 or more tend to be, significant. 3 was an outlier and so forth, all right? So with the decision rule, what we do is we have a parameter called alpha. Alpha is our significance level. Significance level. Significance level. What alpha does for us is that it controls the risk of committing type 1 error. All right. In other words, it creates for us under the diagram what we call a rejection region. So if we say we're looking for evidence that the mean is greater than a particular value, then we want to look in this region. And at some point we set a boundary, and we will call that our Z critical, our critical value. So that critical value is like the same Z critical in a confidence interval. It would be the value beyond which we are now in the rejection region. So we will say reject HO if we're in that region, or we fail to reject HO if we're in this region. Fail to reject HO. So that's called a decision rule. If my Z that I calculate is greater than my Z critical, then we will reject HO. All right? Reject HO. And so that is a critical rule. Now notice that this is a case where if the evidence is actually in the right tail of the distribution. So let's do this. If I had a left tail, meaning that if I wanted to find evidence that the mean was less than a particular value, then I'll be looking in this part of the distribution. And so this would be my critical value right here, critical value. And this area would be alpha, the significance level. So the rejection region, always remember the rejection region is always the size of alpha. This is equal to alpha. So we reject HO, and here we fail to reject HO. Fail to reject HO. Here we will reject HO. Okay. So again, in this case now, because we know this is 0, so what would happen is that if our observed Z value is less than negative Z critical, because any value to the left of 0 is going to be negative, we will reject HO. So that's the rule that we have when we are looking at a left tail test. And let me do the next one here for you, which is a two-tail test. So sometimes we want evidence that the true value differs, right? So if it's different, right here. So if we're looking for evidence that it differs in the sampling distribution, we're looking for extreme values. Always remember with hypothesis testing, we want the extreme values. So if I want values to differ from that middle, I need values all the way down the other end and all the way down the upper end. So either one of those two ends would be evidence for me to support that. So because the total size of a rejection region, which is my risk of committing type 1 error, is alpha, I must divide it into 2, alpha over 2. And it's starting to look like the kind of information we have of a confidence interval. They are actually related, because in a two-tailed test, you could replace it by a confidence interval. All right. So in this case, if this is negative Z critical or positive Z critical, the decision rule is if your observed value is greater than Z critical, or your observed value of Z is less than negative Z critical. Reject HO, okay? So whenever we reject the null hypothesis, our conclusion is that we have evidence to support the alternative hypothesis. So if we're rejecting HO, then we're supporting HA. So if we reject HO, if we reject HO, we are supporting HA. Always remember that. Okay? So that was step 3. Step 4, let me go back one more. So step 4 is supposed to be what we call our analysis. So if we have a Z value to calculate x bar minus mu sigma over root n, or if we have a t value to calculate, this is where we go ahead and calculate it. All right? And step 5 is our decision conclusion. In other words, what do we conclude? So of course, if you reject a null hypothesis, you conclude you have evidence to support HA. If you fail to reject it, you don't have enough evidence to conclude that you have support for HA. Okay? So decision conclusion, your decision is always to reject or not reject HO. That's always the case. Our conclusion is whether we're going to support or not support HA. That's your conclusion. So that's always the case. So that's the 5 steps. If you get those 5 steps, and step 3 is usually the toughest one, it's not a hard problem to do. Okay? So let's quickly go ahead and do a problem. So I'm going to take that very same exam problem because I think we could relate to it very easily. So the idea is that we're given, we believe the population mean exam mark is 66% with a standard deviation of 18%. We take a random sample of 50 and we got an X bar of 80%. So we already calculated what's the probability of finding, in a random sample of 50, an average of 80% if the mean is 66 and the standard deviation is 18. Well, we're just putting that in the context of a hypothesis test. So here's what I'm going to ask in the context of the hypothesis test. At a 1% significance level, is there sufficient evidence the true mean exam mark, or the true mean exam mark, is greater than 66%. So based on the sample that I observed, I'm wondering, well, is it actually greater than that? So let's set up our steps. So step 1, hypotheses. HO, HA. So we will say that the true mean is greater versus is not greater. True mean is greater versus true mean is not greater. Is not greater. Okay? That's Greater. So let's put that in symbols, HO and HA. And always remember that we are hypothesizing about a population parameter, not a sample. So please don't use X bar. So we want to say the mean is greater than 66% versus the mean. If you're a skeptic, you'll say, it's not greater than 66%. So that is step 1. Easy? Cool. Step 2. Let's go. So step 2, we have the following. We want our test statistic. So the test statistic is a normal distribution because we know that the population is normal, sigma is known, so the sampling distribution is also normal. Folks, all of this is the same. We're just putting it inside of a 5-step procedure, but it's like as if we're going to calculate the probability of observing the sample that we did. That's step 2. Step 3, decision rule. So the thing to keep in mind with the decision rule is that we need to know what the sampling distribution is and whether or not it's a right tail or left tail test. So step 3, decision rule. So if we draw this, so is it in the right or in the left that we look for the evidence? Because we are interested in getting proving that a sample mean is greater than 66, it means that we have to look for evidence in the right tail. And so our critical value will be somewhere in the right, so that will be Z critical. And then because it's a one-tail test, this entire region, the rejection region, is alpha. And remember, alpha is the risk of committing type 1 error. We want to make sure that we limit the chance of rejecting the null hypothesis when it is true to only the value of alpha. So in this case, the value of alpha is 0.01. I could tell you from the top of my head because I know it, that is 2.33. 0.01, all you need to do is to look up the 0.01 in the table and you will get 2.33. Or you could look up 0.99 in the table and get 2.33. Okay, but it's on the positive side. So our decision rule will be, so this is reject HO. And then of course here would be fail to reject HO. FAIL, to reject HO. All right? And so we'll say if Z, our observed value, is greater than our critical value, which is 2.33, reject HO. Otherwise, fail to reject HO. All right? That's our decision rule. So one tail test in the right tail. And you know how you know if it's the right tail? If you look at your alternate hypothesis, you want mu greater than 66. Greater, look at the point of the arrow, right tail. If I wanted less than, it would be pointing left tail. If I say not equal to, then it could be either tail. All right? Right now, it's in the right tail. So let's look at step 4. The analysis. And so with the analysis, we just calculate the value of the test statistic. So Z observed, X bar minus mu, sigma over root n. And so it would be 80 minus 66. 18 divided by the square root of 50. And that is 5.50. Okay? So that's a pretty big Z value. That's the same 5.5 we found before. Pretty big Z value. All right? And that we could compare to the 2.33. So clearly, if you go back to the diagram, you will see that with 2.33, it will be in the rejection region. 5.5 will be in the rejection region. And so we know what our conclusion is going to be. But let's go a step further. Let's find a p-value. The p-value is just the probability associated with this, right? So p-value. P-value, in this case, is just the probability that z is greater than or equal to 5.50. Now we know our table has the largest value, 3.09, and at 3.09, the area in the tail is 0.001. So at 5.5 is going to be a lot less than that. Let's look at it. All right. So what we're saying is that at 3.01, no 9, sorry, this area is 0.001. Question is, where is 5.5? Well, it's beyond that point, 5.5, which means that this little area in red is less than the area in blue. And so in this case, this here is our p-value. It's just the probability associated with the sample. Okay? So our p-value, or prob value, some books say. So that p-value is smaller than alpha. This is alpha. Right? Sorry. No, that's point. No, I'm looking at the wrong thing here. Alpha we said was going to be 1%. But I was just comparing the 3.09, 5.5, and letting you know that if at 3.09 there's 0.001, then this piece right here would be less than 0.001. That's what I wanted to say. My apologies for that. Okay, but that is also our p-value as well. Last step is step 5. So step 5, we must now make a decision and a conclusion. Always remember what the decision rule is. If you don't have a decision rule, you cannot make a conclusion. So the decision rule is, in this case, if the z value is greater than 2.33. So we could say since z is greater than z critical, which is basically z, which is 5.5, is greater than 2.33, we will reject HO. What do we conclude? We conclude we have sufficient evidence in fact, not just sufficient, we have strong evidence that the true mean is greater than 66%. For sure, absolutely, we have sufficient evidence that the true mean is greater than 66%. All right? Because that 5.5 is just too far away. Okay, it's just too different from 66. Sorry, from 0. Or 80 is too different from 66. So therefore, we need to conclude that that is the situation. We have evidence to reject the null hypothesis. Can we commit an error? Yes. What is the error? Type 1 error, because we reject the null hypothesis. By definition, type 1 is rejecting the null hypothesis when it is true. So we rejected it, so therefore we can commit type 1 error. The question is, what is our risk? So we set the limit of the risk. We set the limit of the risk to 5%. But is that our real risk? So alpha, not 5%, sorry, 1%, 0.01. That is the limit of the risk of type 1 error. Okay? As a limit. But is that the risk we're actually taking? Answer is no. The risk we are actually taking, the actual risk, is your p-value. The actual risk is the p-value. And in this case, the p-value is less than 0.001. So that's the risk that you're taking. Think of it this way. If I told you, if I gave my kid $10 to spend at a fair, and they came back and spent $5, that's great. They didn't violate any rules, right? So they met my conditions. But if they spent 15, then they had to borrow money from somebody, and that would be a violation. So it's kind of like this. I'm allowing you to take up to 1% risk. But when you calculate the p-value, all the risk you need to take is less than 0.1%. So in that case, you are pretty well within your limits to reject the null hypothesis, because the risk that you're going to take is going to be small. All right, and so that in essence is the 5-step procedure. All we have to do now is to get ourselves or our heads around the different procedures that or the different permutations that could happen. So for example, if instead I wanted evidence that the mean differs from 66, so what would happen in this case is that our test statistic would be the same, but our decision rule would be different. So if I wanted to test HO, HA, mu was not equal to 66 versus mu was equal to 66, then what would happen is my decision rule, not equal to 66, could be values like 50, 40, 30. That means that I could be looking for extreme values down here, and then, or high values, not equal to 66, 75, 85, 95. Okay? So in this case, I have a two-tailed test, which means that I must set up my rejection region. My total rejection region must still be alpha, which means I must split it between the two. So if alpha was 0.01, then that means that this is 0.005. This is 0.005. It turns out that that's what? Negative 2.58, positive 2.58. So now our rejection region is, or our rejection rule is, if Z is greater than 2.58 or Z is less than negative 2.58. All right? We reject HO. Otherwise, we fail to reject. So that's really what the difference would be if I changed it from that. Now, the evidence that we have, we would not be trying to find proof that the true mean is less than 66% because we got a sample with an average of 80. So that does not make sense. So we'll not be interested in that case. But what if I got a sample of 60, for example? 60, with an average of 60. Then I could ask the question, do we have evidence that the true mean is less than 66%? So in a case like that, everything else stays the same. The only thing is the data is different. N is 66, 18, and then our sample mean is 60. All right, and then our sample size, N, 50. So then in that case, it would be a left tail test if we were finding this value right here. So alpha will do that 5%, 0.05, just changing it just to a different value. So this is 0.05, 5% in the tail, we have 10, that's 90% confidence interval, so that's negative 1.64, right? Just know it on the top of my head. And so our decision will be if our Z value, so this is our Z critical right here, Z critical. Okay, so if Z observed is less than Z critical, we will reject HO. All right? We would reject HO. And so in that case, we could actually go ahead and compute our Z value. When you do the calculation, so it would be 60 minus 66, 18 over root 50. All right? And I don't have a pre-calculated value for this, so let me see how we would do this here. It would be 6 times root 50, 6 times root 50. Oh. So 6 times the square root of 50 equal divided by 18. So I got 2.35. Still pretty good. Negative negative 2.35. I think. Make sure I got it right. Yes, 3.357 or 3. So that could be negative 2.36. So if you look at that value, where does that fall? So this is negative 1.64. So in here, the rejection region, that value would be in the rejection region for sure. So negative 2.3. I said 3.5, but it's actually 3.6. We could round up to 3.6. Okay, so you notice that it's in the rejection region, which means that its p-value, so the probability of observing that value, should be smaller than alpha. So alpha is 0.05. So let's find that p-value, which is the blue area right here. So if I look up negative 2.36, .0091, it turns out that the area is 0.0091. So let's look at this here. So my p-value, so one-tailed test, is the probability of z less than or equal to negative 2.36. And from the table, that's 0.0091. Right? So what was alpha? Alpha was 0.05. Cool? So then, since the p-value rule would be that the p-value must be less than alpha, since the p-value is less than alpha, that is basically since 0.0091 is less than 0.05, we will reject HO. So if we reject HO in this case, we have evidence that the true mean is less than 66, right? So our decision conclusion, in this case, decision, so that will be a step 5, decision conclusion. So since the p-value is less than 0.05, I've already stated that, reject HO, we conclude we have strong evidence, we could say strong evidence, the true mean value, mean exam mark, is less than 66%. All right? And that's how we do it. So I did one with a one-tailed test for you on the right, one is a one-tailed test on the left, and then if we change it to two-tailed tests, we just simply split alpha between the two. So if you could handle that, then I think that you're well on your way. All right. So we have a couple more examples to do. We're going to do the case where sigma is unknown, so we have to use the t distribution. We're going to do proportion, and then also I want you to keep in mind that whenever you do a two-tailed test, you can use a confidence interval with the 1 minus alpha level of confidence to solve the same problem. You get the same results. So if your significance level is 5%, you could actually do a 95% confidence interval. If it is 10%, you could do a 90% confidence interval, and you will get the same results. Okay? Hypothesis testing is equivalent to confidence intervals when it is a two-tailed test. And two-tailed tests, we're interested in, has there been a change? Are things different? Not one is greater than or less than. These are one-tailed tests. Okay? So please review this, take an example in your book, and try it out and see how it goes. In fact, I believe I had an example that I just went by, but and then also the PowerPoints in MindTap. You could review those and just kind of solidify what I've just told you in your mind so that you have a very good understanding of all the principles that guide hypothesis testing. Okay? Thank you.